So in this video, I will go through how to do some transient analysis or chloride or diffusion simulations that are time dependent. And we can do this by using this method called LinTransSolver, which is short for linear transient solver. And then some quick background to this method. So what this means is that you have your SVE and you let um, some diffusing substance enter through any of these surfaces. And you will have to specify which surface and at which rate. So what this method does is that it solves Fick's second law of diffusion. So corresponding to this equation here. So in the finite element setting, this corresponds to the C matrix that is computed, and this is the K matrix that is usually referred to. And here you will need to set some material parameters. For instance, if you go into cement class, there's this property storage capacity, and this corresponds to this quantity here on this side. So we had that the diffusion coefficient, this property here, corresponds to the D here. And the storage capacity is a factor that goes in this expression here. Now I think here, when we look on Wikipedia, I think the storage capacity equals to 1, so that's why you don't see it here. But in general, there is a constant times this time derivative. So the method solves this equation, and it uses convective boundary conditions. So it's this type of boundary condition. So the flux from some body like this is equal to alpha, which is a resistance, times, here it's the notation is T minus T infinity. And T here is the correspondingly the concentration, chloride or moisture concentration at the SV minus the concentration in the ambient environment, so the surrounding um, concentration, which would then be outside the SV. So the concentration here would correspond to T infinity, and T here would be the solution or the concentration at the actual surface. And then the flux is equal to that difference between those two times a coefficient, and this is some sort of resistance measurement. So that's a quick some quick background to the theory, because you will need to set some properties when you do this simulation. So first of all, you will need to set these properties. So time steps and time size and initial condition. So time steps is how many steps you want to take in time, and the time step size is the length of each time step. So if you have, well, whatever unit you have, if you have the diffusion coefficient measured in terms of seconds, then this will be seconds, or if you have it in terms of years, this will be years. And this is just some integer value, so just a number of steps. And then the initial condition is the concentration at time equal to 0 inside SV. So in this case, I will just use 0 as a reference. And then you have all of these properties that you will have to set. So this is convective coefficient, that's what this is short for, and this corresponds to this alpha parameter here. So this, you can think of this as the resistance, like a surface resistance. And you can set these on each of the SV sides. So here the notation is you have x dot back, and then you have correspondingly, let's see here, sorry, I think there's there is actually a mistake here, so it should be here it should be x, y. Sorry about that. And it's the same mistake over. Let's see, it should be x, y, z, x, y, z, and then x, y, z, x, y, z. Yeah. Okay, so this is how it is. You have x back, and then you have correspondingly x front, and then y back. Oh, this is all wrong, sorry. Front and front. So, and this should be back. Yeah, probably some copy paste mistake here. Okay, so you have x back, x front, y back, y front, z back, z front for both of these, both the convective coefficient and then hum is short for ambient humidity, and this is this value, T infinity, and this is the ambient humidity or the ambient chloride concentrations, whatever value you have outside the SV. Okay, so you set this, so, and again, this is model parameters. So this is something that you ultimately would have to determine experimentally. Because this influences how easy it is for the flux to penetrate through the surface, you could say. And I set the initial condition to 0, so inside the SV, everything is just 0, and the surrounding here is just equal to unity 1. So what I've done now is I've only set x back and x back for these two properties. And this corresponds to this surface here. So x back and x front works like this. So we have the x direction. So x back is this surface that points in the negative x direction. And similarly, this surface is x front, which points, or the normal of this surface points in the positive direction of x. And similarly, if we take z, so this surface here would be z back, and this is z front, if you look at the coordinate system here. Okay, so now I've set that there is flux going in through this surface because I've set some resistance on this surface, and I've set the ambient humidity here to 1. And the remaining ones are just not included, and what that means is that the model will treat the remaining surfaces as insulated, so there will be no flux taking place around any of these surfaces except this one. Okay, so this is just in principle how you need to set this up in order to be able to run this method. Okay, so those are the parameters that you need to set, and then we invoke, or we do the simulation by invoking this method, LinTransSolver, as I said, and then this one takes initial condition and time as input for this method. So time was this structure here, and then we have the initial condition. Okay, so we run the method, and I pause the video now. Okay, so now the computations are done, and if we go into the folder where we have all the files and data stored, we have now this new file, default name, and this is a file where all the results are stored in. So what we need to do now is to process these results for visualization purposes. So this is what I will do in the next clip.